Hello and welcome to this Isaac Physics tutorial on vectors. I'm Michael Quinterio and I'll be your tutor for this afternoon. This is a follow-up to the vectors workshops that we have run in a variety of places across the country. So you'll need to have your copy of the questions from that workshop in order to follow through. We're going to go through a few questions there, and if you've got any particular problems that you'd like to look at or any queries that you'd like to make, you should see that just below this there is a comments box effectively where you can type in your message and that will be sent to me. There is a slight delay on that. I will not get your messages immediately, so don't worry if it seems like I'm ignoring you, but I will get back to you if you send me one of those, so don't worry about it. And what I'm going to do is I'm going to share a effectively notepad with you that I'm going to be working on. So if I just bring that up now, there we go. We can start diving into some of the questions. So I'm going to start on exercise 8, which is kind of a follow-up to some of the questions which you should have done in the workshop about random walks. This is one where we're just kind of looking at it in a slightly different way. So the question says, cosmic rays are charged particles that move randomly in a galaxy as a result of being scattered by randomly oriented interstellar magnetic fields. This process resembles diffusion. In such situations, we can apply a random warp to the cosmic rays reaching the Earth from beyond our galaxy, the Milky Way. Given the dimension of a galaxy as 5 times 10 to the 20 meters, and if the mean free path for a cosmic ray is 3 times 10 to the 18 meters, estimate how long it takes for a cosmic ray to travel across the galaxy. Assume that it travels at almost the speed of light. So we've got a few pieces of information there. We've got the mean free path. Which I'm going to call A. We've got a speed of light, C. And we've got the dimension of the galaxy, which I am going to call R. And so when we've got our cosmic ray moving, it's kind of bouncing around lots of times. And kind of like the average distance is the mean free path. Then we're going to say R is the distance away from the starting point that it ends up. And the total length of the path that it's taken, we're going to call L. So we know, now we've kind of like drawn a diagram, defined everything, now we're ready to actually start tackling the question. So we know that this R, total distance traveled, is equal to the root of n multiplied by A. That's what we got from the random walk. The distance that you traveled away from your start point is equal to your mean free path, mean step length, times by the square root of the number of steps that you've taken. We can also say that we've got this path length, L, which is just the number of steps we've taken, multiplied by the average length of each step, NA. And what we actually want is the time taken. So the time taken for this, T, is simply the distance over the speed. And then we can substitute in. So substitute in for L, gives us NA over C. And then from this one here, we can get R squared equals N A squared. So our N can be replaced with R squared over A squared. We've still got our A and C. Oh, and then we just cancel out, and we end up with R squared over A C. And then we can put the numbers in. Okay, so moving on, we're going to look at the next question. First few parts. So exercise 9. The vector capital R is formed by adding the x components and the y components of the lowercase ri vectors whose orientations are random. So we've got here, we've got R made up of randomly oriented Ri. Part A. If one of these lowercase r subscript I vectors is projected onto a particular axis, explain on average while the projected value is 0. So we can take whatever axis we like. And then if we then have our, actually let's put the image in there. So if we have some Ri and project onto this axis, that's not very well done. Hang on, let's try and get that actually up 90 degrees. There we go. So my projection is here. We know that by mirroring it in this other axis, we can also have, just as equally likely, another vector which is a different Ri. So I'll call this Ri dash with the projection. So if this projection is A, this is minus A. And so the average, obviously the average there is 0. And that's the same for basically everything apart from one directly over here, which is 0 anyway. So yeah. So the average has to be 0. So the question then, what is the average value of R? In this case, we just do similar thing, but instead of having the projections equal and opposite, we just say, well, for each vector in this direction, we have an equal and opposite just as much chance as an equal and opposite one in this direction. So the average of of capital R is just going to be 0. However, what we then go for is R squared, and this is not the vector dotted itself. This is the average of this is the average of R dotted with itself, which is not the same as the average vector R dotted with the average vector R, because this is equal to 0 and this is not. So in this one, we end up with R1, all the individual vectors which make it up, right, to Rn, dotted with itself. And so we end up with two different types of term. One where it's one of these smaller vectors dotted with itself, and lots of those. We also have lots of them which are different things. Because of the random orientation, all these terms here cancel. And so we're just left with, oops, just do n terms of this form where it's the subvector dotted with himself, dot product are the same, and that they are all of length r squared. Okay, so moving on to a little bit further in the book, we are going to look at some of the projectiles questions in the additional questions section. So in all of these questions, we're going to assume that there is no force in the horizontal direction, so we're not going to have any air resistance or friction in there. And in the vertical direction, we're just going to have a constant acceleration downwards equal to g, the acceleration due to gravity in the absence of all other forces. And this means the motion horizontally and vertically are going to be independent of each other, so we can split those up. So exercise 10 says a projectile is fired horizontally off a table at 4 meters per second. It falls towards the ground with an acceleration of 10 meters per second squared, so we're taking g to be 10 meters per second squared there. Calculate the magnitude and the direction of the velocity at these different times. So we'll start off at t equals 0. It just has a horizontal velocity, which I am going to call v0. Time 1 equals 1 second. Horizontally, we can't change that bit. We can, but since we've had constant acceleration downwards, we have a component of the velocity acting downwards. So this has magnitude, this side has magnitude v0, and this side has magnitude g times t1. And in fact, we basically, for all other times, draw the exact same thing with no change in the horizontal component of the velocity. But this component is proportional to the time. And so for a generic vector here, I can call this V horizontal, and this V vertical. So this is a vector with components of magnitude VH and VV and an angle theta from the horizontal. Now these are right angles to each other, the horizontal and vertical components. So magnitude of V squared equals to VH squared plus VV squared. And we can see that tan of theta is opposite over adjacent. How is the velocity related to the flight path of the projectile through the air? The velocity is a rate of change of displacement over time and is always at a tangent to the position. Okay, so that was exercise 10. Remember, if you've got any questions, do put them in the box underneath. And if you're not seeing the box, remember to log in to Isaac Physics first. I'm going to clear this out the way and move on to exercise 11. Two projectiles are fired horizontally in opposite directions at 3.0 meters per second and 4.0 meters per second. At what time are their paths at 90 degrees to each other, and how far have they fallen? This can be done by sketching the diagrams of the vectors and algebraically using vector notation and vector dot product. So I'm going to start by sketching. So at a generic time, I've got my two things. So I've got, I'm going to call this VA. And I'm going to draw these touching because when the paths are at right angles, that means the velocities must be at right angles because the velocities are in the direction of the motion at that point. So we've got that hit there, and I can just finish that triangle. But for the separate V and VB, because we've got a constant acceleration downwards of G, the vertical component downwards will be GT, and the horizontal component will not change. So what we know from these is that we can actually replace this entire top here. We say that this is UA plus UB. So we have from this, using Pythagoras on this right angle triangle, UA plus UB all squared equals VA squared plus VB squared. And we can get those by using Pythagoras here. For instance, on this velocity VA squared equals UA squared GT squared. Similarly, VB squared equals UB squared plus, again, GT squared. And from there, it's just a case of putting the numbers in and combining these equations. The other way of doing it is by vector notation, in which case we can write VA as UA GT. So I'm taking these directions as positive, and then VB equal to minus UV because it's traveling in the opposite x direction, GT. And if these two are perpendicular, you get that the dot products must be equal to 0 because A dot B is A B times, make sure I get this right the right way around, cos beta. And the other way of doing dot products is basically multiplying the respective x components together and adding that to the multiplication of the y components together. So VA dot VB equals UA times minus UB plus GT multiplied by GT. And then you can, and that's equal to 0. Then you can put the numbers in and solve from there. Okay, and so moving on to question 12. I won't go through this entire question. I'll just go over a bit of it because I don't think we have time to go through the full question. I mean, this is a very much good one for practicing and setting up your problems. Because it says, a projectile is thrown at an angle of 30 degrees above the horizontal from the top of a cliff. It hits the level ground below at an angle of 60 degrees above the horizontal. If it is in the air for 20 seconds, how far from the foot of the cliff does it hit the ground? Use G equals 9.81 meters per second squared. So we start off by drawing it. So what have we got? We've got a cliff. The stone is thrown off this initial velocity U, which is at an angle θ1, I'm going to call this, to the vertical. And when this lands, that's not very good drawing. I'm getting it too flat here because it says 60 degrees. So let's draw there. That's close enough. The final, and we have our angle here, θ2, which are the angles given in the questions. This is obviously a right angle. This is going to be my distance traveled horizontally. This is going to be distance traveled vertically. And let's split up our vectors. So we have U vertical, and U horizontal. And then my VF of VH. And one thing that you should note here is that UH equals VH because there's no change in the horizontal velocity. Now there are a couple of different ways you can do this. One is by working out when this hits here and kind of working out the time taken for it to come down this distance, so you can work out SH afterwards. Another way of doing it actually is to pick the point at the top where the velocity is entirely horizontal, which is, of course, equal to the horizontal component of the initial velocity. And think about the times there. So yes, lots of different ways of solving this, but the important thing is setting up your problem at the start. Okay, that concludes our workshop, our online tutorial. I hope you found that useful. Remember, the form will still be live for a while, so if you do have any more questions, put them in there, although it'd be impossible to contact you unless you tell us how to. You can also use the contact us form on the website. Thank you very much, and we hope you continue to enjoy using Isaac Physics. Good night.